Yeah, hi, I'm Thomas, and welcome to my talk on noise-assisted synchronization in networks of coupled Mathieu-Duffing oscillators. So this is joint work with Professor Balachandran from the University of Maryland in College Park. So just to set the stage, synchronization has been observed in a variety of systems. So natural systems such as fireflies, human brain activity, or cells. Additionally, we have seen synchronization in technical systems such as the famous clock experiments or power grids. And the synchronization phenomena is most often linked to the Kuramoto model, and that's why I want to motivate it in the next slide a little bit. So the Kuramoto model models the interaction of many oscillators where the dynamics are now given by this equation here. And in Kuramoto's analysis, he assumes that each single agent, each single cell, has a dynamics with a limit cycle. And phi now measures or indicates the phase along this limit cycle for each individual cell. And then the whole network is then arises then if we couple the individual cell dynamics with this coupling function here. And while this very general model can be deduced by viewing the underlying phase-space theory and introducing averaging arguments, we wanted to have a more mechanical traceable system and to study the effects of noise in the end. And to come up with a mechanical equivalent featuring those key ingredients of the limit cycle oscillations, we have used parametric excitation. And we were inspired by the following experiment here, where we have a set of oscillators, so cantilevers here, where there's a tip magnet attached, and on the opposite side there's a fixed base magnet. Now the base magnet can be moved with a linear actuator, which varies then the gap size between those two magnets. And this gap size variation can now influence the linear stiffness of the cantilever beams. And this now, if we vary this excitation periodically, this can give rise to parametric excitation. And the oscillations, arising oscillation of this cantilever can be modeled by the following dynamic mechanical model. Second order differential equations, where we have some parametric excitation here, nonlinear restoring forces, and coupling between those individual cantilevers around the base. Additionally, we have the possibility to add noise, and we're going to study the effect of noise in the next couple of slides. And in the experiment, the noise can be introduced by an electromotor which is mounted to the shaft, not included on this picture, and this can now rotate the whole assembly, and this can introduce noise. Now, the deterministic intuition of this model is that if we now carefully choose our frequency of parametric excitation, omega here, this can destabilize the trivial solution, so the Q equal to 0 solution, and then give rise to limit cycle oscillations. And we have analyzed these equations now, starting from the simplest ingredient is the single cell dynamics. So now in the limit of no noise and no coupling, we end up with a single cell dynamics of the following form given here. And if we then now assume weak nonlinearities, weak damping, and weak parametric excitation, and select the parametric excitation frequency omega to be close to the 2 times the natural frequency, so the first parametric resonance, the method of averaging needs the following set of equations. So just to convince you that these equations are useful, we have compared them with the full solution. So the full solution from numerical time integration shown here in green, and underlying the green curve solution here, we should have a blue one which practically overlaps. They're indistinguishable in this, at least in these figures. So the average solution captures the overall dynamics quite well. Additionally, we get the envelope equations from the average, but also we can solve the average equations for fixed points. So this is the purple curve here, the purple line here, and those fixed points then give rise to the indicate the limit cycle oscillations. So these are the stable limit cycle oscillations. And we can solve for them, for this set equations, analytically, and also get the stability type of these limit cycle oscillations in analytically. So we can compute the following bifurcation diagrams. So for small parametric excitation frequencies below the first primary parametric resonance, we have this, the origin is stable, and this is the only stable solution, and all solutions decay to the fixed point. Now if we approach parametric resonance close to 2 here for this parameter configurations, the trivial solution becomes unstable, and we see a rise of 2 stable steady-state solutions. So here shown in this inset here, we have an unstable, so the origin is unstable, and we have 2 stable limit cycle oscillations. If we increase the parametric excitation frequency further, we observe that the trivial solution becomes stable again, and 2 unstable, additionally unstable steady-state solutions arise. So this is the phase space shown for such a configuration, for such a parametric excitation frequency. We have the 2 stable solutions, 2 unstable solutions, and the stable trivial solution again. Now we have looked at the effect of noise for the single cell. So this is the noisy, the single cell dynamics with noise now on the right hand side. And we have more specifically looked at the set where we have 2 coexisting stable steady states, which we have denoted by A and B. Now, if we add noise to this dynamics, small noise, we can observe the following. So for example, if we start with an initial condition close to the attractor A, we will generally stay close to the attractor for a while. However, after a while, the noise accumulates, and one will observe an escape to attractor B. Similar things can be observed if we start close to attractor B. We will stay close to attractor B for a while, and then after a while we will escape to attractor A. And so we have now computed the mean escape time, so how long it takes to transition from A to B, or from A to B, or from B to A on average, and we observe that the mean escape time here is approximately the same for both from the transition from A to B and the other direction. So from the stochasticity, none of those solutions A or B is favored in any sense. We have further advanced with studying the network dynamics. So these are the network dynamics without noise. And again, we can use averaging with the assumption of weak forcing, weak nonlinearities, weak coupling, and weak parametric excitation. Close to the first parametric resonance, we have the following set of equations, which cannot be solved closed form anymore, but one can have numerical solutions. And just to give you an idea of the structure of the solutions, now if we have in the uncoupled limit, if we have, for example, in the uncoupled limit, let's say for a parametric configuration 3 solutions for the single cell, now if we go to the network, we're going to end up with 3 to the power n solutions. So we see an exponential increase of the number of solutions in this system. And now if we start to increase the coupling strengths, we see that the number of solutions disappear through Pitchfork bifurcations. And we have looked at the norm of the solutions a little bit more closely now here for a network of 10 oscillators. So here for 0 coupling strengths, we have this 3 to the power n number of solutions. So this is a number here for k to kc equal to 0. We have 3 times 3 to the power 10 solutions. And if we now increase the coupling strengths, we see that the norm of the solution generally decays, and some of those solutions disappear through Pitchfork bifurcations. Additionally, we have looked at the order parameter. So the order parameter gives us an idea of the phase alignment of these of all the oscillators. So the phase is defined as the arctangle of the position divided by the velocity, and then the order parameter gives us an average phase, gives an alignment of the average phases. So if Rx equal to 1, all the phases of the oscillators are the same, and we denote this as perfect synchronization. Lower order parameters are lower than 1, denote not complete synchronization, and 0 means that there's complete dysynchronization in the whole network. And we can see that for all the solution, the order parameter takes a value of 1, 2, 3, 4, 5, 6 different values, and remains constant for all coupling strings along all solutions. And we can also plot these solutions, how they might look like for the network of 10 oscillators. Now if we advance to a higher order network and start adding noise to the system, for random initial conditions, these are now the steady state distribution of the phases after a long while for a number of trials. We observe that the phases of the oscillators tend to alter between two values here. So each trial we don't observe perfect synchronization. However, now if we add noise to the whole dynamics, we observe that the phases here shown perfectly synchronizes for each and every case. And here this gives us the order parameter now for a number of trials, up to 100 trials. We see that in the noisy case, each and every case we have achieved perfect synchronization. Whereas when no noise is added, the order parameters varies all over the place, is on average about 0.4. So the addition of noise promotes synchronization in this oscillator network. So this is so just to summarize my talk, we have studied synchronization in mechanical systems, and we have realized synchronization. We have realized it by using parametric excitation to create this limit cycle oscillations, which are the key ingredients to study synchronization. The method of averaging has revealed that in the system we are looking at, we have a multitude of limit cycle oscillations, and the addition of noise promotes synchronization. That's what we have seen in the very last slide. So future work, we envision to carry out experimental investigations with the experiment I've shown you in the very beginning of this talk. Additionally, we are working on on a direct connection of our mechanical model with the more abstract Kuramoto equation. And additionally, it would be interesting to study the effect of disorder, so parameter disorder, on this effect. And so more specifically, we are wondering about what happens if the eigenfrequencies are not perfectly the same. So there's variation in the eigenfrequency in the network. Thank you very much for listening, and if you have any questions, feel free to reach out anytime. Thank you very much.